So this is a continuation of example 1b. Okay, we're gonna do engine torque on shaft caused by the shear stress. Previously we know the shear stress already. Now we're gonna use the shear stress to calculate torque. If you found that this is very familiar, it's actually this is the same thing that I'm doing right now. Okay, you can head back to the old videos on this videos by the name of all this. Okay, and then so to find this is actually power, we need to get the torque. So we're gonna look at the torque. So the torque itself is actually torque equals to force times radius, and this force can be in terms of 2 pi r l shear stress. Okay, this is the equation. You make sure you remember. Okay, so this is radius of the shaft, and then this is the thickness, and this is shear stress. So by it should be Newton meter. Okay, this torque is Newton meter, this is meter, and this is Newton. Am I right? This is Newton per meter square. Sorry, this is Newton per meter square. If you want to know why, you just head back to the old videos. But nonetheless, with this understanding, let's go back to the previous one. Okay, so this is what we have over here. We know that this is the force also, and therefore this is the length of the shaft, and this is the at the surface of the shaft, this is the radius. Okay, and then this is the shear stress. So we know our shear stress is some values, 4342.9. If you remember our Google value 4341. Okay, if you still don't believe, come back to our thing 4342.9. Okay, so I use the same values, I just throw it in. And then this is actually 2 pi r, 0.03175. How do I get that? This is actually this is the radius r, 3.175. Sorry, it's actually this one, 0.0762. It is still the bearing. The diameter of the bearing is 0. If you were to come back over here, the diameter of the bearing is from here to here, right? This is the diameter. So the radius is definitely this divided by 2, right? Since the diameter of the bearing is 0.0762, so we have 0.0135, 137 or something like that. So if you take a look, it should be, it is, where are we? Yeah, it is over here, 0.03175. Okay, so repeat again. If let's say 0.0762 divided by 2, 0.0381. Okay, so hold on. I make myself wrong. This is not r. Okay, this is r. This is radius. R times r. Okay, is actually r square. Okay, so don't be fooled by the same corresponding thing, because this r is not this one. Okay, this one is actually shear stress, which is this one. Okay, and then 2 pi r l times r is actually 2 pi r square l. So 2 pi r square l. Okay, so this is the length of the shaft. So if you head back to the length of the shaft, you know that this is 3.175 times 10 to the negative 2, which is in other words 0.031675. And you have to do that, you get 1.258. Okay, so this is your shear force. I mean your torque. Sorry, your engine torque. So this is the engine torque required to turn, okay, in order to overcome the shear stress. That's what I mean. And then the next one is using the torque to determine the engine power. So this is the same thing that we have done earlier in the previous lesson, long time ago. Okay, you will see that you get angular velocity times force is equals to power. Okay, so how do you take the force? You know that the torque itself is a torque. What am I talking? So hold on. It's angular velocity, okay, times the torque force. Okay, so I should write it as torque force, not torque. If you were to doubting me, this is a very big word from Google. Okay, the power is equals to the torque, okay, times the omega, the angular velocity. Okay, maybe I need some. Yeah, just trust me lah. Okay, so power is equals to torque force times angular velocity. That's it. Okay, So this is also reflected over here. If you don't trust me, you should also trust my notes, or the notes come from my lecturer. So yeah. Anyway, so where are we? So we have this one over here. So this is the work done per time. So if your work done over time is actually power. Okay, if you want to prove it again, and divided by time, what do you get? Great job. What do I have? Power equals to work over time. That's something I found. So this is the power is equals to the torque force times the what they call angular velocity. So this is, make sure you know that this is work done over time. Okay, I think there will be a trick question of talking about that. So is equals to torque. You know our torque is 1.258 Newton meter. Then you know that our angular velocity is you know this is 14.36. This is your linear velocity we actually derived long time ago. Okay, back in the old days. 14.36. Where are we? Okay, hold on. Yeah, this is our velocity. Okay, so this is actually the first part. Taking that the zero gradient, calculate the amount of shear. What am I doing? Where am I over here? Yeah, this is your linear velocity. Okay, and your angular velocity is some 3600. If you still remember how we derive. Okay, so this is your linear velocity. So we have 14.36. So this is where I have the value. And then r is actually the radius of the shaft. So 0.0762 divided by 2 is actually 0.0381. So which is over here. So if you do that, you have 474 watts. So you have a power now. So lastly, we talk about the Reynolds number. So if you talk about Reynolds number, you're gonna use this formula. So why is this formula different from the other formula that we're talking about? Okay, so this is actually okay. So this should be rho v average velocity L. Okay, if you remember this is average velocity, I call you to remember. And in this case, this is not pipe, this is only plate. So therefore, we can actually use the average velocity of this one. Okay, so this is the velocity that we derived earlier. If you don't know why you just press back a few minutes ago. I explained. Okay, so this is 14.36 meter per second. And then this is the viscosity, which is also given 9.6. And then the density is actually 920 kg per meter cube. Okay, so I'm not gonna just show you the density of 920 kg. And then there is L over here. If you remember our Reynolds number is either D or L. So in this case is length. So this length is actually this length over here, A. So please remember this length over here is actually because you're talking about examine the flow Reynolds number. The flow Reynolds number is actually this length because you're going across this thing. So the length itself is just taking this one. That's all. I don't know why you don't want to take the radius, but yeah, just take the length. So in this case, if it's a shaft, you just take the length. No idea why. Okay, but if you remember the pipe thing, you're taking the diameter, right? Taking this one. Okay, so this is the diameter. So if for the plate itself, similar thing, although it's not that similar, you're taking the length itself of the fluid. You're not taking this direction of the you're not taking the length itself. I don't know why, but that's the case lah. Okay, this is just a brief explanation. Nonetheless, what I took is actually the A value, which is this one. Which is this one and this length. A equals to 3.175 times 10 to the negative 5. So I have this value over here. So as you can see, this numerator is actually 10 negative 5. This denominator is 10 negative 3. This comes from the viscosity value. So if I have to cancel, okay, I have 9.6 only, and then this one will become negative 2, right? So if negative 5 divided by negative 3, you get negative 2 over here. So if I were to calculate, okay, I should have the value. So I should have this value over here. So it's 920 times 14.36, the average velocity. Make sure you know about the plate, times 10, times 10 to the negative 2. Okay, I have this value. Something is wrong with my calculator. I should use Google again. Damn it. Hold on. Okay, let's do it again. Okay, we have 920 multiplied by 14.36 multiplied by 3.175 multiplied by 10 to the negative 2, 10 to the power of negative 2. What do we have? We have 419.4556. Okay, and then divided by the viscosity, which is in this case 9.6 now. Okay, 43.69. So with this value, you know that this is a laminar. How do we know? We can actually head back to this page. Hold on. Yeah, it's at this page 20. If Reynolds number is larger and is smaller than 2000, is laminar. Okay, so the range, it all depends on which range you take lah. So in this case, you take 1500, but should be 2000 in your notes. So whatever. So whereas this value is so small that it is definitely laminar lah. So with this, we have finally finished the example 1b. Okay, take note that this is the flow of the Reynolds number of the flow, the oil flow. And then, so I'll see you in the next video for Bernoulli's equation. We have cleared away all the things. So yeah. So next video we'll talk about it, but not today. I think I gonna go slack. I'm very tired. So we have cleared away chapter 7. So we have 3 more chapters to go. Okay. This chapter 8 is kind of like heavy. Okay. And then chapter 9, which is a little heavy, and chapter 10, which is very heavy. So I'll see you in the next video for that. Bye bye.